This is my second math video of the day. I want to get this done and over with. This is Unit 7, Lesson 5, using a model from a sequence. Check in. What are the three forms that a sequence can be given in? And the answer is a list of values, a graph, or a function that models the sequence. Here is example 1. Mr. Bernie's shop sells red roses at a full price of $10 per dozen, with a 5% discount for every 5 dozen purchased. Find the price per dozen roses by using the model f of n is equal to 10 times 0.995 raised to the power of n, where n is the number of sets of 5 dozen red roses purchased. So before we move on, if you're like me and you don't have a math brain, where they got this 0.95 is. This is how much they're paying for each dozen roses after they purchase 5 dozen, okay? So if $10 is how much they pay for a dozen for the first 5 dozen, for dozen 6 and on, they get this discount. So they're only paying 95% of that $10 because they get a 5% discount, okay? It's kind of convoluted. So before solving the problem, notice that n in the model represents the number of sets of 5 dozen red roses purchased, okay? We're not talking about single red roses, we're talking about sets of dozen roses. The customer is purchasing 17 dozen. So there are n equals 3 sets of 5 dozen roses, okay? Again, what the cow, what the cow, what the cow, okay? So for every 5 dozen purchased, you get a 5% discount, okay? So sets of 5, they're purchasing 17 dozen, so they have 3 sets of 5. So n is going to equal 3 for this problem, okay? They're trying to make it super complicated, and they're succeeding. So first, substitute 3 into the model to calculate the price per dozen, okay? We're going to do that down here. So we have our formula right here. I'm going to grab my markers if I can find them. Okay, and what we're going to do is we're going to take our formula, which is right here, and we're going to go f of, we have 3 sets of 5 dozen roses to get the discount. Okay, so we're doing f of 3 is equal to 10 times 0.95 raised to the 3rd power. So grab my calculator, bink, and we're going to go 0.95 times 0.95 times 0.95. That's 0.95 raised to the 3rd power gives us this big long decimal place thing. We're then going to multiply that by 10, which is just going to move the decimal place 1 space. That means the cost per dozen when purchasing 17 dozen red roses is $8.57 per dozen instead of $10 per dozen because we get the discount. Okay, I hope all that made sense to you. Remember that $10 would be the cost at full price. With the compounded 5% discount, the total cost of the order, how we would find that is, we know that it's $8.57 per dozen, and we're buying 17 dozen. So you would take 8.57, we stop there because we're dealing with money, okay? And we're going to multiply that by 17 dozen, and that would give us $145.69. Now, if we were paying $10 a dozen, then we'd pay $170. So we did save money. If we take $170 and subtract $145.69, we can see that we saved $24.31. So we basically got 2.5 dozen roses for free. Okay? I know there's nothing else this complicated. Don't stress too much. Here's example number 2. Carbon dating is a technique used by archaeologists to estimate the age of organic remains. When organic remains are found, archaeologists measure the level of carbon-14 in the organic remains. That information, along with the known half-life of carbon-14 being about 5,730 years, is used to calculate the age of the organic remains. This is how scientists estimate how old dinosaur remains are. Okay, this is a very frequently used thing in biology. Shown is the graph of the percent of carbon-14 remaining over the number of half-lives elapsed. So this is the percent remaining, and this is the number of half-lives. So use the graph to rewrite the sequence of the percent of carbon-14 remaining over the number of half-lives elapsed. So they want us to write the sequence as we're going from half-life to half-life to half-life, okay? So the sequence representing the percent of carbon-14 remaining over the number of half-lives elapsed is the list of y-coordinates of the points in the graph. We obviously don't want to do the x-coordinates because that's just 1, 2, 3, 4, 5. That's the number of half-lives. We're looking at the percent of carbon-14 remaining. The y-coordinates are 100, 50, 25, 12.5, 6.25, and then it goes down to 3.125, okay? Now, the next thing it wants us to do is estimate the age of organic remains if there is 25% of the carbon-14 left in the remains. Okay, so we're going to come over here to the percentage. We're going to find 25%, which is going to be right there. Oh, look at that. It gives us our answer right there. It tells us that we're going to be at 2 half-lives. Okay, there's going to be 25% of the carbon-14 left. And it wants us to estimate the age of the organic remains. It's going to be 2 half-lives old. Is that what it's looking for? Organic remains of 25% of the carbon-14 left correspond with the 0.225 on the graph. This means 2 half-lives of carbon-14 have elapsed. Yay! That was worded weird. I didn't know if I was on the right track. Therefore, the age of the organic remains can be estimated as follows. This is a typo. This should be a 5. Okay, 5,730, which is given us right here, times 2 is equal to 11,460 years old. So if they found something that had carbon in it, some organic life form that was this old, it would be approximately 11,460 years old. Okay? Here's question number 3. What percentage of carbon-14 should archaeologists find in organic remains that are 22,920 years old? So now we're going to work backwards. Okay, we know if something's this old, we need to divide it by this to see how many half-lives we're dealing with. So let's go 22,920 divided by 5,730, because that's how long one half-life is. Okay, so we should be at about 4 half-lives. If we come up here, then we should be at about 6.25%. Okay, because that's the point right here on the graph. Okay, at 4 half-lives, we're at 6.25%. Now we need to find the function that models this graph. So we're going to have to go back and think about our last lesson where we did arithmetic and geometric sequences. Okay, so is this one changing with addition and subtraction or with multiplication and division? Well, to go from 150 to 25, it's obviously division, right? Or multiplying by a fraction, however you want to think about it. So this one has to be a geometric sequence. So the geometric sequence is a sub n equals a sub 1 times r, which is the ratio difference, n minus 1. Okay, so we have some of this information already. Our initial value is going to be 100% of whatever. Okay, so at 0 years, it's going to be 100% of that. The rate of change is they're multiplying by 1/2. So I'm guessing we're going to change it to a function. So it's f of n is equal to a sub 1, whatever that is. It's going to be whatever is at 0, 100, times the rate of change is 1/2 times 1/2 is going to cut it in half every time. Okay, and we're going to multiply that by n minus 1. I believe this is what the formula will look like. It's going to be, oh, they put 100 in, times 1/2 over x. I used x instead of n. You can use any number, any letter here that you want to. Okay, so they did put the initial value of 100 in there because they're using percentage in this case. All right, here's another check-in. Which representation of a sequence gives a visual image of how the sequence behaves? A graph gives a visual representation. Now, I typed in sequence for my search term for all of these pictures, and it took me forever to figure out what this was. I thought it was something really gross, like fish scales or something. They're sequins. Sequins. And it gave me sequins for sequence, thinking that I am that bad at spelling. Look, he's covered in sequins too. That's pretty bad. Here's question number 1. This is your turn. The function g of n is equal to 500 times 1.05 raised to the power of n models the sequence of the end-of-year balance of an investment account. So first, interpret the numbers 500 and 1.05 and the variable n in the context of the problem. And second, list the first 5 elements of the sequence. Pause it, figure it out, then come back. So interpreting all of this nonsense, this is the total money in your account. This is your initial deposit into your account. This is the rate of interest. You're getting an additional 5% every year. And this is how many years you've had the account. Okay. Now, to get the first 5 elements of the sequence, you would start by putting a 1 in here. So it would be 500 times 1.05. So that would be like, so your first number would be 500. And then it would be, let's grab my calculator because I don't trust myself. I think it would just be 505, but I'm a moron. So 5 times 1.05 gives us, I didn't do that right. I did 1.5. 500 times 1.05. Oh, it's 525. It's a good thing I didn't just assume I knew what I was doing. Okay, so then to do the next one, you're going to take 525 and we're going to multiply it by 1.05, which will give us an extra 5%, and that would be 551.25. And you do that to get 5 terms, okay? So 500, 525, 551.25, blah, blah, okay? 500 represents the principal, your initial deposit. 105 represents the annual interest rate of 5%, and N represents the time in years. I am a smarty pants. Okay. It helps if I give myself stars. Here's question 2. The function g of n is equal to 500 times 1.05. N models the sequence of the end-of-year balance of an investment account with a principal of $500 and a 5% compound annual interest rate, which is what we just talked about, in which n is the length of the investment in years. Find the balance of the account after 15 years of investment. Pause it, figure it out, come back. So n is going to be equal to 15 this time. So I'm just taking the formula we have and entering 15 in the place of n. So 1.05 raised to the power of n. Now I know that most calculators have the ability to raise things to a power, but I don't know how to do it on this one, so I'm just doing it the hard way. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, we've got this big, long majigger now. We're going to take this, our answer, and multiply that by 500, and it's going to give us that. So the balance of the account after 15 years is going to be $1,039.46. We know where to cut it off because we're dealing with money. $1,039.46. Oh my gosh, guys, I am a rock star. Okay, here's practice question 1. A small town started to track its population in the year 1950. Each year that passed, the town's population increased by 44. So 1950 is when we started. Each year we're adding 44. The function f of n is equal to 495 plus 44. So in 1950 we obviously had 495 people. Represents the town population n years after 1950. What was the town's population in 1950? What is the projected population in 2030? Sorry, I gave you an answer. Pause it, figure it out. We know that this is the population in 1950 because that's our initial value always. So there's 495 people in 1950. Now we need to figure out the difference between 2030 and 1950. So 2030 minus 1950 gives us 80 years. Okay, so this means n is going to be equal to 80. So we're doing f of 80. Can you tell I'm not wearing my wrist brace today? 495, I can actually write somewhat legibly, plus 44 times 80. Calculator, come back. So 44 times 80 gives us that, plus 495 gives us that. So we're expecting 4,015 population. 4,015 people in 2030. That's a big difference. Here's practice question number 2. The cost of a large cheese pizza at a local pizzeria can be modeled with the function c of n is equal to 16.5 plus 2.5n, where n is the number of toppings that can be added on. If a customer has $35 to spend, what is the maximum number of toppings that they can add to their large cheese pizza? Pause it, figure it out, come back. So 35 is the total they have to spend. That's going to replace right here. So we have 35 in the place of c of n is equal to 16.5 plus 2.5n, and we're going to solve for n. So let's subtract 16.5 from each side. And I don't trust myself, so I'm getting a calculator for this, because by now you should know how bad I am at math. 35 minus 16.5 gives us 18.5. Okay. So that means that we have $18.50 to spend on toppings. Each topping costs $2.50, so we need to divide each side by 250. 250. And that means this is how many toppings we can get. 18.5 divided by 250 gives us 7.4. Now we can't order 0.4 of a topping, so we can order 7 toppings. Okay. Practice question 3. Carbon dating is a technique used by archaeologists to estimate the age of organic remains. This is all the same stuff we talked about before. The graph models the percentage of carbon-14 remaining over the number of half-lives elapsed. Choose the statement that describes the meaning of the coordinate point for 6.25. We're dealing with this point right here. What does this mean? So your options are when 6.25 half-lives have elapsed. That's not right, because that would be over here somewhere. These are the half-lives. So this one's out. There is a 6.25% of the carbon-14 remaining. Yeah, it's 6.25%. When 4 half-lives have elapsed. Yup. Let's double check we don't have any others that could be right. If 6.25% of the half-lives have elapsed, then 4% of the carbon remains. No, they're not both percent. That doesn't make any sense. 4 half-lives remain when 6.25% of the carbon-14 has elapsed. This isn't elapsing, the time is elapsing, so that one doesn't make sense either. Check. An insect population is growing such that each new generation is 2.5 times as large as the previous generation. Suppose there were 54 insects in the first generation. The function p of n is equal to 54 times 2.5 raised to the power of n minus 1 represents the insect population for generation n. Interpret the meaning of p4 is equal to 843.75. Okay, I'm not going to tell you how to answer this, but you need to interpret this. So if we put P4 right here, that means that N is being replaced with 4 in this formula. Okay, so if you replace this N with a 4, this is the answer that you would get. So what does that mean down here? There were 843 insects in the 4th generation. There were 844 insects in the 4th generation. There were 4 insects in the 843rd generation, or there were 4 insects in the 844th generation. So what you need to decide is which of these numbers, the 4 and the 8, which is the generation and which is the population. And then you need to decide, is it appropriate here to round this up or down? Okay. So with normal rounding rules, this one should actually be part of the next section, but with normal rounding rules, you would go up because this is a 7. But do we have another full whatever this is to round up to 7? If this doesn't quite make sense yet, don't answer this until we move on to the next section. Okay, come back to this one. Here's quick check question 2. The sequence 3.75, 7.5, 11.25, 15, 18.75 represents the total cost a customer pays at a taqueria based on the number of tacos ordered. This means that the total cost for one taco is $3.75. For 2 tacos, it's $7.50. For 3 tacos, it's $11.75, and so on. What is the maximum number of tacos that can be ordered if a customer has $100 to spend? Okay. So in order to solve this, there's 2 ways you could do this. You could keep following this pattern. Well, first we need to find the pattern. So 375 to 750 is, let's get a calculator. I want to try that hard. 7.5 minus 3.75 gives us 3.75. So they added 3.75 the first time. Okay, let's go 11.25. minus 7.5. That's also 375, so there's another add. We're looking for a pattern here. Let's go 15 minus 11.25. That's also 3.75, so there's our pattern, okay? We're dealing with an arithmetic sequence where your difference is 3.75, okay? So from this, we can make a formula, which is what I would choose to do. The formula for an arithmetic sequence is going to end up being f of n is equal to a1, which is your initial term, which is 3.75, plus n minus 1 times your difference, which is 3.75. Sorry, I ran out of room. Okay. So this is what your formula would look like. So if you have $100 to spend, the $100 replaces this, and then you would solve for n. That's one way to do it. Or you could just continue this pattern, continue adding 3.75 until you hit $100. And then you could count like 1, 2, 3, 4, 5, how many tacos there would be. But obviously you're going to have to do a lot of those. You will get the correct answer. It will just take time. Okay. Here's the second half of the lesson. Example 1, Sasha is investing $1,000 into an account that pays 2% interest. This can be modeled by the function f of x is equal to 1,000 times 1.02 raised to the power of x, where x represents years and f of x represents total money in the account. The table records the total amount of money in the account for the first 5 years. Shink! How much money would Sasha have in his account after 10 years? So in order to solve this, you would just take your formula, put 10 in for x, and then solve. So using the formula that describes Sasha's investment and evaluating for x equals 10 years, the answer is 1,218.9944199. Since this example describes a monetary situation, you would conclude that Sasha has $1,218.99 after 10 years. You're going to cut it off right there because it's money, and money doesn't go past the hundredths place. Okay. Here's a check-in. In what type of situation is it particularly important to report sequence analysis with high levels of precision? High levels of precision are necessary in situations involving money, since money is typically reported in dollars and cents, rounded to the nearest hundredth, even if no directions are given. Additionally, situations involving objects such as people, animals, or any other data for item that can be counted must use whole numbers. For example, a solution of 3.7 people would not make sense. It would need to be rounded to the nearest whole number. Okay. Here's example 2. A ball is bounced from the ledge at the top of a staircase that is 150 inches tall. After each bounce, the ball returns to 3/4 of its original height. The bouncing ball can be modeled by the function f of x is equal to 150 times 3/4 raised to the power of x. What is the height of the ball after 6 bounces? Round your answer to the nearest inch. So just like last time, you're going to replace x with 6 and solve. Okay, this geometric sequence decreases as it is multiplied by the common ratio 3/4 each time. The height of the ball decreases each bounce. Use the formula and evaluate it for x equals 6 bounces. So for f of 6, we're going to have 150 times 3/4 raised to the 6th power. Calculator time. So 3/4 is also 0.75. There's 1, 2, 3, 4, 5, 6. Okay, gives us that big long decimal place. We're going to multiply that by 150, and we end up with 26.69677777777. And it says to round it to the nearest inch. So 26.6 would go up to 27. Okay, 27 inches. Here's another check-in. Dwight came to help me finish this. Okay, why do geometric sequences frequently have decimal solutions that need to be reported with precision? A geometric sequence involves multiplying the previous term by a common ratio. When the common ratio is not a whole number and involves fractions or decimals, the following terms in the sequence will also be fraction or decimal solutions. Example 3, Raquel is organizing an event at school where students must sit in the rows of the school auditorium. The first row has 20 seats, the second has 25 seats, the third row has 30 seats, and this pattern continues for the entire 10 rows of the auditorium. If each class has 23 students, how many full classes can attend the event? Wow, look at this. This is an arithmetic sequence since the total number of seats in the row increases by 5 each row. We're dealing with addition, so it's just arithmetic. It can be modeled using the sequence 20, 25, 30, 35, 40, 45, 50, 55, 60, 65. Notice this sequence has exactly 10 items since this is the total number of rows in the auditorium. By adding each of the terms together, so 20 plus 25 plus 30 plus 35, blah, 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 the total number of seats in the auditorium is 425. To determine the number of full classes that can fit into the auditorium, take 425 divided by 23. That's how many people are in each class. And your answer is 18.47. Only full classes are allowed to enter. Raquel could not have 0.47 of a class enter the event. Thus, 18 full classes could attend. This is a situation where analyzing sequences and reporting solutions with precision is important due to the nature of the situation. When dealing with objects like people and animals, you may not be able to use rounding rules. You may have to round down even though you would usually round up. For example, 27.8 people might need to be rounded down to 27 people. This is what I was trying to explain with that first quick check question. So let's go back and peek at that really quick so I can show you what I was talking about. So in this case, you have this decimal place here. So whatever this is does it make sense when you have population and generation to round this up? No, because you don't really have 844. If it's population, you don't have 844 bugs. You only have 843. And if it's generations, you can't say it's the 844th generation because it's not. It's the 843rd generation. So even though math rules say we would round this up, in this context, we would not. Okay. Let's come back over here and see if I can figure out where I was. Cry, cry, cry. Okay. Question number 1, this is your turn. Reed is volunteering at a local children's hospital and handing out candy to each of the patients. Reed plans to hand out 2 pieces of candy to each child and expects to see about 70 children. If each bag of candy contains 30 pieces of candy, how many bags will Reed need to buy? So first, describe the sequence in the situation and write a formula to model the total amount of candy Reed will give to children. And second, determine how many bags of candy Reed should buy and report the result using an appropriate level of precision. Pause it, figure it out, come back. Okay, this is an arithmetic sequence since Reed is handing out the same number of candies to each child. It's going up by addition, plus 2, plus 2, plus 2. The total number of candies given out increases by 2 each time he sees a new patient. The formula f of x equals 2x models the total number of pieces of candy given out at the hospital. Using the formula and evaluating for x equals 70, Reed would need 140 pieces of candy. To determine the total number of bags needed, divide 140 by 30. That's going to give you 4.66666666. Since Reed cannot buy 0.666666 of a bag of candy, the solution should be rounded up to ensure he has enough candy for all of the patients. Reed would need to buy 5 bags of candy to have enough. So in this situation, you would, with math rules, you would automatically round up. But if this was 4.33333333, Reed would still need to round up, because you can't be short and have a poor sick kid come up and be like, I want candy. You'd be like, sucks to be you. There isn't any. Here's question 2. The fish population at a local lake has been exposed to a dangerous virus. Before the outbreak, there were 220 fish in the lake. Now each week, half of the fish die from the virus. How many fish will remain? That made Angie sad. How many fish will remain after 6 weeks? Pause it, figure it out, come back. This is a geometric sequence as the terms in the sequence are multiplied by 1/2. The fish population could be modeled by the following sequence: 220, 110, 55, 27.5, 13.75, 6.875, or by the formula f of x is equal to 220 times 1/2 raised to the power of x, could be evaluated for x equals 6. To determine the solution is 3.4375. So either way, you can find the answer. Attending to precision is important in this situation as the whole number of fish should be reported. There would be about 3 fish remaining in the lake after 6 weeks. Okay, end of the lesson. Practice question 4. A pendulum swinging back and forth loses momentum and distance with each oscillation. The total distance the pendulum swings on the first oscillation is 12 inches, and the distance of each consecutive oscillation is 2/3 of the previous distance. What distance will the pendulum travel on the 5th oscillation measured to the nearest whole inch? So again, there's 2 ways you can solve this. You can just do each iteration and find out for 5, or you can write the formula. There's only 5 of them. I'm just going to figure this out. So 12 times 2/3. So 2/3 is 0.66666666. So I'm just going to do 12 times 0.666666. It's going to give us 7.99. 7.99. And it wants us to go to the whole inch, so doing 2 decimal places should be fine and shouldn't screw anything up. 7.99 times 0.666666 gives us 5.33, we'll say. 5.33. We'll use math rules and round up there. Okay, we're going to take 5.33 and times it by 0.666666. It's going to give us 3.55, 3.55. And now we just need to do it one more time. 3.55 times 0.666666. Going to give us 2.37. But we want the whole inch, so 2 inches. Practice question 5. There are currently 3.5 inches of snow on the ground. If the weather forecast predicts it will snow at a rate of 1/4 inch per hour over the next day, how many inches of snow would you expect to have on the ground after 7 hours? Round the answer to 2 decimal places. Pause it, figure it out, come back. Again, you can do a little table chart, or you can find the formula. I'm lazy, so I'm doing the table chart. We're starting at 3.5, and this is 1 shunk. At 2, we're going to add another 1/4 inch, so it's going to be 3.75. At hour 3, it's going to be 4 inches. At hour 4, it's going to be 4.25. At hour 5, it's going to be 4.5. At hour 6, I guess this is hour 0. I should do this right. So this is 1. This is 2. This is 3. Pay attention, don't be like me. This is 4. This is 5. Okay, so this is 4.75. At hour 6, we have 5 inches. And at hour 7, we have 5.25 inches of snow on the ground. Look at that. I'm so smart. Okay, quick check question 3. The function g of n is equal to 275 times 1.032 raised to the power of n models the sequence at the end of year balance of an investment account with a principal of $275 and a 3.2% compound annual interest rate, in which n is the length of the investment in years. Find the balance of the account after 13 years. So Take this formula, replace n with 13, solve, and you'll get your answer. Quick check question number 4. Analyze the explicit formula of the arithmetic sequence a sub n is equal to 3.7 times 1/2 plus 1/2 times n, and report the ninth term rounded to the nearest tenth. So you're going to replace n with 9, and then you're going to round to the nearest tenth and find your answer over here. Here's quick check question number 5. Towns bought a personal watercraft for $6,500. If it depreciates in value by 13% each year, the situation can be modeled using a geometric sequence with a common ratio of 87.87, which is started in the table. Okay. How much will the personal watercraft be worth after 2 years? Round the answer to the nearest dollar. So to get from here to here, they multiplied by 0.87. Okay, so you're just going to do that again and then find your answer right here. And Holga's losing her mind. Thank you so much. Empowering early childhood development through play and discovery.